Let me just tell you about electrical potential and potential difference. In order to check this first relation, that the work done by the internal force is equal to minus du and the work done by the external force is equal to du. For this, check my last video, okay, how to find this. Okay. So now let us start with the charges. So let us say that you have a charge q and it is fixed, okay, and there's another charge q naught and we are moving this charge from one point to the other, okay, and this is done by this force, which is some external force, okay. And the displacement is by these through small vectors, by these small vectors. So this is the displacement vector from here to here. Let us say that this point is A and this point is B. So we are moving from A to B. Now from your experience you can say that because it is a positive charge, it is also a positive charge. This charge will have some force on this charge, okay. So this charge will experience some force due to q naught will experience some force due to q, and that force will be away from the charge because they are of the same charge, positive and positive. So this will be Fe vector, which will be away from the charge. Now in this case, Fe is your internal force. So the work done by the internal force will be Fe vector dot displacement is in this direction, so it will be ds vector. And you know that the work done by internal force is minus du. So when we talk about gravity, then it is gravitational potential energy, but here U is electric potential energy, electric or electrostatic potential energy. I think it should be electrostatic. So then we also know that the electric force per unit test charge is equal to electric field. Okay, so this implies that Fe vector is equal to q naught E vector. So let's just replace it here and bring this negative sign towards this side. So it will be du will be equal to minus Fe vector dot ds vector, okay, or we can also say it is minus q naught E vector dot ds vector, okay. So then in order to solve it, we need to take an integral of both the sides. So take an integral here and integral here. Now we are moving from point A to point B, so this integral will be from A to B, A to B, okay. So from here we'll get UB minus UA, which is equal to change in potential energy will be equal to, and charge is a constant, we can take it outside, integral of E vector dot ds vector, okay. So this is the change in potential energy. Let me use PE for potential energy, okay. Now electric potential is defined by change in electric potential. Change in electric potential is defined by delta V is equal to change in potential energy per unit charge. Therefore, delta V will be equal to minus integral of E vector dot ds vector when we are moving from A to B. Okay. So change in potential energy, and this is change in potential. Okay. Now suppose that we are moving from a very far away distance. Let us say that A tends to infinity. We are moving from an infinite distance to a point which is B. So we are moving from infinity to B. So this potential difference will be V infinity minus VB minus VA, which will be equal to minus, let's take this expression, okay, so it will be final minus initial upon Q naught. Okay, let's take it in this manner so that it is easier to understand. So initial is infinity, final is B. So this is final, this is initial. So final will be VB minus, now at infinity the potential will be 0, and so final will be potential energy, and this is 0 upon Q naught. So we get VB is equal to UB upon Q naught, or B and B. So it means it will be true for every point A, B, B, C, C. So in general we can say that electric potential is potential energy per unit charge. So the units now, it has a unit of volt, it is energy, so it is joule, and it is coulomb. So 1 volt is 1 joule per coulomb.